Now the people watching will
Yeah,
never have your
is a
credentials.
is a perfect way to start the presentation for anyone watching at home. Quaternions suck. You already knew this. Yeah. So I feel like the typical introduction is we go over like the origin of the idea, and then we talk about like gimbal lock and 2D examples, and then we talk about 3D math, and then we finally get to like the good stuff that we want to learn about, which is how to use quaternions. And from my own experience, I kind of like decided by the U-learning goals part that this was not something worth putting effort into. Like you get to the 3D vector math and you're like, this sucks. I hate this. I don't want to continue this lesson. And so once you get to the actual good stuff, you're already in that mindset of quaternions suck. And so this is a perfectly valid thing to feel considering like mathematical scope of them, but just for like 10 minutes, bear with me as I give you some cool examples of what we can do with quaternions. Yeah, so instead, we're just gonna look at the applications first. It's good to know your history of maths, but who really cares right now? We're just gonna go over how to use them. You can look that up later. 2D rotation examples are not super useful, and you should probably already know what U-learning goals are. And if you don't, just Google them for the next like 2 minutes and you'll probably understand. But yeah, it's important to know what problem we're solving. So we're still going to talk about gimbal lock, and the 3D vector math is still kind of useful to understand the concept. But yeah, so first, the big take-home message I hope you get from this is you don't need to fully understand quaternions to use them effectively. I know you're maybe thinking, Dane, I want to implement quaternions in my custom game engine with new physics and all that jazz. That's fine, good excuse, but even then there's probably libraries or someone's covered it better than you can. So better just leave this one to the people that study maths. Yeah, and also disclaimer, everything I'm about to tell you about has a lot of math going on behind the scenes that we're probably not going to get into. So the first big thing that you can do with quaternions is rotate things. You're probably familiar with this concept already, given that quaternion rotation is a thing, and that's generally what they're associated with. More specifically, though, they're rotations that are applied to vectors. And even more specifically than that, they're rotations that maintain the magnitude of a vector. And so you can sort of think about the vector coming from an origin, which is that red dot there, and then it has a distance. And you're rotating a vector sort of within a sphere. And I want you to imagine that sphere whenever we talk about rotating a vector, because it is kind of rotating around that origin. And because quaternions maintain the size of a vector, it is always rotating within that sphere. And so you can either think of it from the perspective of the vector is rotating within the sphere, or there's a point on the sphere that is rotating around the, what do you call it, circumference? Maybe that's not the word for a sphere, but it's rotating around the outside of the sphere.
Circumference.
Yeah, cool. Yeah, so the other big thing that they're known for is slurping, which is like the cousin of the lerp. I wish these looped, but they don't. And so you can kind of see here, they're kind of do the same thing where they're interpolating along a line, but then there's a little bit of a difference between slurp and lerp when it comes to like covering the same distance. Yeah, and these are from there if you want to check them out. And so if you imagine this as the outside of the sphere, you're sort of interpolating along that. And we're going to see that it's kind of difficult to do that with Euler rotations and other kinds of ways of doing this. You can still get the same end result from doing those, but they don't really lend themselves to doing this interpolation along a sphere. Next, yeah. Yeah, and then another thing to keep in mind when we're talking about quaternions is that they always take the shortest path. So if we're rotating from the top of the sphere to sort of the right axis of it, quaternions, if you say move from here to here, they're going to take the shortest path to get there. They're not going to do some weird spirally thing around the globe. They're not going to go all the way around the back. They're not going to take like a route down and to the right. They're always going to take the shortest path. And that's all the crazy math that we're not going to get into. And you can kind of think of this like you're planning a flight around the globe. You don't want to just draw a line when it's all flattened out. You want to find the path along the curvature that gets you there the quickest. Yeah, so that's another takeaway is Quaternions always take the shortest path. Yeah, and this is one of the examples I did for a project for GDD2, I think it was, where we just had this menu and there was different like menu things around the scene. And we just did Quaternion.slurp to move around the scene when different buttons were pressed. And it was super fast, super easy. You just move from one position to another with time. And yeah, you could do this with each individual angle and say, so we know at this one, the rotation is facing this way. We know at this one, I think, what is it? Pitch or no. One of the rotations is facing that way. So we can just interpolate between those, but that's like, yeah. But each of those is like its own angle. And so if you had like a more complex rotation, it'd be a lot more difficult to program that in. And it would also not follow the slurp rule. It would probably be a little bit more linear, which as we've seen is slightly different. Yeah, another thing you can do with Quaternions is angle axis or axis angle. People use them interchangeably pretty much. So this is, you define an axis that you want to rotate around, and then you move that angle around that axis. So in a really simple case, this would just be rotating something like around the Y axis. And so you would spin in place, like if you were in a spinny chair, you would spin around. Super easy to understand. But you can also do more complex things where if it's like pointed up by like 45 degrees and then to the left by 30, you could still spin around that axis with the same amount of ease as if it was the up vector. Yeah, and then there's the similar rotation thing on transforms in Unity. That's two angle axis, where you can find the angle and the axis from the existing rotation of the Quaternion. I don't know exactly what this is useful for, but I'm sure there are some uses for it. Another big thing Quaternions are really good for is pointing at stuff. Because Quaternions always take the shortest path, you can fairly easily have like a camera or something that's moving with the player in a, it's not just snapping to the position it needs to be in, it's sort of lerping and doing a smooth movement to point at your player or something. So yeah, they always take the shortest path. You do slurping on them and they're continuously pointing where you want them to point, which is very useful. And yeah, sort of a Unity, I don't know if Unreal has this or any other game engine, but there's this look rotation method that's pretty useful, where if you define a forward vector and an up vector, you can just say Quaternion.look rotation, and it'll do all that interpolation for you. Let's see. So yeah, in this case, this was the spline example that I was talking about earlier that I did for my position. It turns out it's really easy to find the tangent on a spline. And so that's sort of our forward vector at any given point. And then the up vector isn't always going to be facing directly upwards, because you can see this ramp sort of points in a different direction. I can't see comments, but I can see them coming in. So sorry about if I'm not answering questions. But it sort of tries to figure out where the best up vector will be and where the best right vector will be, which has been super useful for aligning things to that track and aligning things to a spline. Yeah, and if you didn't do this, there's a chance that the track would like spiral to get to where it needs to be. So yeah, Quaternions are always unit Quaternions. As I don't think I've actually mentioned that, but I think it's been at the bottom of my couple of the slides so far, which means when you're applying Quaternions to vectors, you're always doing it through multiplication. And so you're applying, I think the order is you have a vector and you multiply it by a Quaternion, just the way the vector math works out. But these also can chain together. So you can have multiple Quaternions multiplied by each other, and it's multiple rotations that are happening. And the thing to keep in mind here is that it's associative, but not cumulative, which hopefully some a semblance of what that means, which is just you can apply them in the same order with different parentheses versus like a reversed order doesn't have the same effect. So if I were to like rotate my arm like maybe up and then over, it'd be a little different than if I rotated it over and then up. So this is where it gets a little bit more complicated and mathy. So if you're familiar with, what are these called? Imaginary numbers and the concept of moving into the imaginary plane by multiplying by I. So yeah, if you're in the real plane and you multiply by I and then you multiply by I again, you're back at -1. Quaternions do follow a similar sort of logic in their four numbers. And so I think as you can see here, there's still sort of that idea of a circle in their multiplications. And there's also like much larger circles going on and everything sort of connects and rotates back onto itself, which I think will become a little bit more clear later on. I guess this is a 2D example, don't sue me. And then something to think about is summation and why doesn't it work? After all, you can add vectors and you can add scalars together. But remember that all quaternions are unit quaternions. And so if we add them together, that would no longer be the case and they lose a bit of their meaning there. I don't really have a great explanation without diving deeper into like the mathematical concepts, but think of it like adding two vectors that are direction vectors. You don't really preserve the final direction if you do that, because there is like a magnitude that is associated with that direction. And so if you were to add them together, it's usually not a good idea. Hopefully that made a little bit more sense, but just don't add quaternions. Most game engines don't let you do it. This is another thing quaternions are great for, is converting between local and global space. So this is just a really simple thing I have in one of my projects because I had to do like it was kind of similar to a transform, but not really. And so to define a forward vector, you just multiply the standard forward vector by the rotation of the object. Super simple. And then to convert between local space and world space, you would multiply by the rotation again. So any position that is relative to the object, if you multiply it by its position and then if you multiply by its rotation and then add the position, you can get its local coordinates or its world coordinates. And you can sort of think about what this would look like with Euler angles, where if you had to convert between local and global space, what would that even like look like? Like you would have to multiply by the pitch, multiply by the yaw, and then the roll, and then you get into ordering effects, and it's just a mess. Whereas Quaternions, super simple, multiply by rotation. Can I actually see comments? I can. Cool. Does if you try hard enough. Cool. I have notes here, and I forgot what I was supposed to talk about here. Okay, so yeah, as I mentioned earlier, I was doing this thing with simulations and Euler angle output into this flight tracker. And the problem was gimbal locking, which I'll mention in a second. So occasionally they would do really weird rotations and sort of like when the pilot would go up for like go up and then down for a nosedive, weird things would happen when they were going down where they would start spinning even though they're not spinning in the simulation. And to solve this, what we would do is we convert the angles that are coming in to quaternions and then convert the current position and the current rotation that was in Euler angles to a quaternion as well. And that way we could just simply slurp between those two angles and it would give a nice smooth transition between them. And so even if the simulation read out that we had rotated a full 350 degrees, quaternions take the shortest path, and so it would only rotate the 10 degrees, and that was much cleaner than doing the full spinning thing. So yeah, just taking advantage of the fact that quaternions always take the shortest path, even if the Euler angles are doing crazy things. Yeah, and this kind of brings me to a next point of why don't we use quaternions all the time? I'm talking about them like there's some great mathematical genius thing, but in fact, there are some limitations to them. The primarily of which is that there's no winding up of the axis and that they always take the shortest path, which may not be a good thing for animation. And so this guy, Paul Neely, summarized it pretty well, I thought, so I just posted his quote there. So if you have 2 keyframes and you set one at, let's say, I think he does it 1 on 0 and 1 on 360. What you would want to happen between those 2 frames is it to like come out and then do a full 360-degree rotation. But because quaternions are always taking the shortest path, they're like 360, that's just 0. What are you talking about? I'm just going to stay where I am. Nothing's going to happen. And so, yeah, that wouldn't be super great if you were animating. And then the other reason we don't use them all the time is that they're super easy to understand. Like pitch, yaw, and roll, you can Google that in 2 minutes and sort of like, okay, I understand what this means. You could probably explain it to a 4-year-old and they'd be like, cool, I get it, for the most part. Unfortunately, you are not 4 years old, and so you have to learn complicated math. I'm sorry. There's also the issue of representing them. So I know in the Unity editor, you do like the position is XYZ, and then you do the rotation as XYZ, which is the Euler angles, and then scale as XYZ. So just to maintain some consistency. But in fact, behind the scenes, it is working with quaternions. Any questions so far before we get into the super duper mathy stuff? I will actually open up the chat again if I can find it.
It's mostly just me complaining about how you pronounced Euler.
I know. I said it how many times? Is it Euler or Euler? Euler.
You said it. You said it twice the right way.
Yeah.
Back to back.
Euler.
Euler. Who cares? Quaternions are better.
I like Euler because you can make puns with it.
Oh,
That's my hot take.
I like Quaternion because it's not the name of a mathematician.
Wow. So yeah, just wanted to review real quick. All quaternions, unit quaternions, quaternions always take the shortest path. Big takeaways, you don't need to understand quaternions to use them effectively. Like, this is a pretty simple concept. Rotate around an axis. Point at a thing. Interpolate between 2 rotations. Like, these are not super complicated things to mentally get your head around. It's just the math behind them sucks for some reason. And yeah, always multiply. And if you want to understand the math, wait. No, we'll go back. All right, I have that later. Cool, pitch, yaw, and roll. We're going to talk about Euler angles now. So if you weren't already familiar, Euler angles are pitch, yaw, and roll. And so that's 3 rotation matrices that you multiply together, just like you would multiply quaternion matrices. But the issue that this creates is a thing called gimbal lock. And if you don't know what gimbal lock is, you'll run into the Obadiah Stane, I think his name is. You run into the same problem as Obadiah Stane, where you'll be 500 feet in the air, and you'll be like, gimbal lock? What's gimbal lock? And your whole program is going to crash. Bad thing to happen. So it's important to understand why we're doing quaternions. So this is a kind of nice image representation of it. But essentially what's happening is that because you're multiplying them in a certain order, one of the axes of rotation will get locked in with another. So the center rotation here, the one in red, the Y gimbal, is happening relative to the first. And so if you were to rotate the first gimbal, and so now it's aligned with another one, those would be rotating on the same axes. And so if I do this first rotation and now the gimbals are locked, this variable here and this variable here are doing exactly the same thing, and I've lost a degree of freedom. And so now you can think about what would happen if I wanted to rotate around what was the y-axis. Like, how would I point at anything that say, can you see my mouse?
Yes.
Okay. So if I have like an object here that I want to point to or look at, like I can do with a quaternion, how would I get the object to rotate in that direction? I have to rotate the red axis 90 degrees, and then I have to rotate the green axis 90 degrees, when really I just want to rotate one of the axes 90 degrees. And there's also some ambiguity about which way to do that and what's the most effective way to get there. And yeah, so this is kind of similar to the plane example I was describing. So you'd get up to an orientation where you're pointing straight up or straight down, and all of a sudden rotating around the y-axis causes you to spin even though you're not really spinning. And yeah, you can see this in the matrices as well. The middle rotation is happening relative to the first, and then the last rotation is happening relative to the middle. And right now you might be thinking, just reorder them, easy. Well, it's the same problem. It's the order that you apply them in always has an effect on gimbal lock, I guess. So you can try and be clever and avoid it, but eventually it will happen. Some real world examples of this are this spinning death contraption. Oh my God. I don't know how to pause it, but at a certain point, all three gimbals are locked. And so rotation of any single one of them causes the same action, which is why it kind of like snaps and like slows down and speeds up all of a sudden. So you can see it kind of looks like it's slowing down for a little bit, and then it sort of speeds back up, and then it slows down again. And that's just, that's caused mostly by gimbal lock, even though each axis is moving at the same speed constantly. And then another, I think this is Apollo 11 or 13, one of them, whichever one had problems with the fuel explosion while in space. When they were doing that whole, we're in trouble, Houston, we have a problem situation, they were a little bit out of control. And so their gimbals were actually very close to locking, which would have left them kind of dead in space without a way to orient themselves. Yeah, so this is a real world thing that also happens. And you can't, as I did a little bit of research into, you can't just add another gimbal, because you're going to run into the same issue of one of the axes in the middle can rotate and become the same as the outer two. And yeah, here's another 2D analogy that I think is a little bit more intuitive. In this example, you kind of have 2 degrees of freedom. So you can either go north or south, or you can go west and east. But when you get to the North Pole, west and east have no meaning, and you're only able to move north. But if we were to define 2 new poles, say in like Rochester and Sydney, Australia, we would now be able to move relative to those 2 new poles, which is kind of what quaternions are doing when you're orienting yourself in 3D space. They're kind of adding a 4th axis that you can move along. So you can orient yourself if you get into this situation. West and east have no meaning. It is true. How much time do I have? Oh, I have so much time. Cool. Next, we're going to talk about the math. Ooh, everyone's favorite part. I'm going to preface this again by saying you don't need to fully understand quaternions in order to use them effectively. Andrew, come back. You arrived at the worst time.
Hello.
Cool. If you think I'm full of shit and that quaternions are actually something you want to dive into, check out 3 Blue, 1 Brown's videos. He's much more qualified than I am and has spent much more time dedicated to making these concepts a little easier to understand. So yeah, check him out for sure. That being said, one of the resources I looked into was this book, Game Engine Architecture, which I'm sure we've plugged at some point before. And they sort of talk about the reasoning behind quaternions from a game engine perspective. So if you were to do Euler angles, you would need 9 floating point values to represent a rotation, which is excessive considering there's only 3 degrees of freedom, which are pitch, yaw, and roll. And then rotating a vector requires a vector matrix multiplication, which involves 3 dot products or a total of 9 multiplications and 6 additions. And ideally, you'd like to do that in a little bit less expensive way. And yeah, again, and then point 3 there is to do with the slurping attributes of quaternions. So ideally, you'd like to be able to interpolate between 2 rotations, and Euler angles don't really let you do that in a neat way. And yeah, and so he says, thankfully, there's a rotation representation that overcomes these 3 problems. It kind of looks like a 4D vector viewed this way, and it behaves a lot differently, as we've seen. And you usually write them as QX, QY, QZ, and QW. I forget if I've shown examples of them before. And then, yeah, here's that thing about all quaternions are unit quaternions. They follow this property of if you square all them up and add them together, it equals 1. Okay, there it is. That all seems super complicated and mathematically deceiving, but if you were to actually look at the X, Y, Z, and W values of a quaternion, it's not super complicated looking. So if you have a quaternion identity, it would just be 0, 0, 0, 1, because if you could think about X, Y, and Z as being no rotation, and then 1 is that 4th variable that has to be 1 because it's a unit quaternion. And then if you're rotating on the x-axis, it'd be -1 there, and then 0, 0, 0, because you're not rotating around any of the other axes. And then the W gets set to 0 because it doesn't need a value. If you're rotating 180 around Y, it's the same thing but Y. 180 around Z, same thing but Z. And if you're rotating 90 degrees around one of the axes, you would sort of do that thing where it's like √2/2. And so this isn't super complicated looking, I think, when you express them in this way. And so again, that's the X, Y, Z, and W. And they're all adding up to 1 when squared. And yeah, there's also ways to convert them between Euler angles and quaternions. And so sort of the notation that gets used is X, Y, and Z are a vector in their own right because they are X, Y, and Z coordinates. And so you can often express quaternions in terms of a vector and a scalar, with the scalar always being W and then the vector being just the X, Y, and Z components. And you don't need to know this thing at all. So I'm sort of getting to the end of my presentation. There's this very famous formula that was carved into a bridge somewhere for some reason. But I say, who cares? We're not math students. We are game developers, and it's much easier to just use quaternions in a cool way than to understand all of the math behind it. And yeah, so what I wanted you to take away from this is you don't need to fully understand quaternions to use them effectively. Quaternions always take the shortest path, and all quaternions are unit quaternions. And hopefully by repeating that multiple times, you remember it. Any questions?
Why is math evil?
Math isn't evil. It was just invented that way.
So a quaternion is like a transformation you apply to is it both a transformation and an orientation? Like it's like the state and the thing you do to that state?
Yeah, I don't think I have an example in here, but there is like a matrix that you apply, sort of like
you just multiply a quaternion that represents the state with a quaternion that represents like the transformation to like get the end state. That's like a 4x4.
yeah.
thing,
So you have
right?
the, what is it, like you have the position vector that you would maybe multiply to get a rotation, and so it would have to be at least 3 tall. But then quaternions, I think it's actually like a 4x4 matrix that you use. I wish I had put an example in here. I didn't think about that. But yeah, essentially it's a 4x4 matrix. And I think somewhere in here, it looks more like this 4x4 matrix here. But there's like way more math behind it. Ferris Boiler's day off. Oh my God.
I remember this is just a me thing, but like a lot of physics professors, like when you do calc physics, they're just like, yeah, you should kind of know this. When I had calc-based physics one in my old school, they were just like, yeah, first week we had to do stuff like this. It was awful. They really do want you to like know your sines and cosines and quaternions.
We have libraries for that. Like I honestly don't think you need to know how quaternions work. Like if you can just know that you can slurp them, you can do angle axis stuff, you can make them point at stuff. Like using those concepts, it's very Googleable.
We had
to
the
find a solution.
We had the technology.
Yeah, like it's not unimportant to like understand the history behind them and the actual math, but we are not math professors. Like, why? No, don't convert them. Please, I beg of you. Really? That all made sense? I'm shocked.
No.
I can end the presentation. But yeah, if you have any questions, feel free to post in like miscellaneous help or something. Look rotation. Yeah, I showed off the sword game you made, Andrew.
I don't know why I'm using text chat.
Yeah. Yeah, meeting adjourned. But if you want to stick around, you can. Also, if you have a topic you want to talk about, please hit us up and let us know, because we're always looking for new topics. And Quaternion Day only happened because we ran out of topics. So got them.
Or if there's a topic you want to hear about.
Yeah, if
We
there's a topic
had
you wanna
other
hear about.
topics. I pitched doing one on like jobs, and then Dane was like, "Oh no, you just did a talk. Don't do it." So
We just talked about
we
jobs.
had presentations. We had presentations, but no.
We didn't have any good presentations.
I mean, have you guys done one on the pixel art yet? Or is that like something
Yeah.
that happened last?
We-
Yeah.
I mean, we did a general.
Yeah,
Did
you
we do an art one?
one.
I'm just thinking about
Yeah.
Pico.
I definitely did one last semester. I think I gave it.
You
or
drew
with-
something. Okay.
I did it in conjunction with you.
Yeah, we did
we got the
something.
tomato icon from it.
Was that
No,
last
that was the
year,
first one.
though?
That was the
was
a while
first
ago.
one.
That was geez, that was
Or second
time
one.
is fake yet again.
Yeah.
I understand that this could be less important, but have you ever considered a story development?
I could do that.
Narrative development.
I'm not trained in that. I like to think I am, but I'm not.
I mean, me, Kaylee,
I-
and maybe Eddie could put together like a twine one too.
Fair enough.
I made a twine for my roommates for Christmas. That was pretty fun.
Wine.
Yeah, I was being ambitious about it too. I'm like, I'm gonna make this twine, and then I'm gonna draw all these pictures for it, and like,
You stop recording.
yeah. No, this is important content.